Okay, so my name is Javier Blasco. I'm the General Chairman of the Plant Engineering Workshop, and it's my pleasure to introduce you to Alex Matveev, who is going to discuss about several practical topics of pipe stress analysis using past start proof software. So Alex, when you want, I will be here to help you with the questions and everything. Okay? Thank you, Alex.
Okay, thank you. So we can start right now, yeah?
Yes, please go ahead and start. It's already 3 minutes past 12, so we can start already. Okay, thank you.
Okay, thank you everybody for joining us. So in this workshop, I will show you several practical topics of pipe stress analysis, and I will use the past Star Prof software and past Nozzle Fem software for nozzle finite element analysis. A little information about past Star Prof. It is developed since 1965 and widely used in Russia and some other countries. We had about 3,000 users, active users, and user interface in English, Chinese, and Russian language. We have 32 piping codes included in the software, and we have about 18 codes for wind, seismic, snow, and ice codes. So let me show you the StarProf software. In this workshop, I will just work with StarProf software, and I will not show a lot of presentations, just working with software. So the first topic is how to consider the nozzle and vessel flexibilities during pipe stress analysis, and how to create the nozzle vessel junction point. So let me create the simple model in StarProf. I will use ASME B31 free code, this one. The ambient temperature, for example, will be 10 degrees. So now I create the first pipe. It will be, for example, 1 meter. I'm sorry, I will use the meters and millimeters, but it's very easy to change the units, but it's more comfortable for me to use meters and millimeters, so I will use these units. We can take the pipe from the database. I will use shadow 20 and nominal diameter 200 millimeters, this pipe, corrosion allowance, and material. This is material database. I will take this steel. The pressure, for example, 1 atmosphere, and temperature, for example, 150 degrees. We will calculate the pipe weight automatically. I will specify the fluid density. And also we can specify the insulation, the density of insulation layers. But I will not use insulation. I will use 0 insulation date. We have some additional properties here. I will leave it the default values. So now click OK. This is our first pipe. Then I add the second pipe. For example, -1 meter. Next pipe will be by Y direction. And here we will put anchor. Now I will add the bend in this node. I have a lot of type of bands, but I will use just ordinary band. Here you can see the stress intensification factor, and you can see that the greatest stress intensification factor is for short bands, then long bands, 3D bands, and 5D bands. The lowest stress intensification factor is for 5D bands. I will use long band. Without flanges. Now I can copy the band and paste it into another node. Now let me save the model. Now we can copy this model into the clipboard, and now I will use the mirror function. I will use this mirror function. The mirror will be YZOY, this plane, and I will copy the piping. Okay, we have piping like this. Now I add another pipe. It will be, for example, 4 meters.
Excuse me, Alex. There's a question in the chat. Maybe you can read it and try to answer before you proceed.
Okay, one moment.
It was sent to me, just to me. The question is the ambient temperature for fabrication or erection? What shall be set for analysis, ambient or erection? What shall be considered for nozzle check?
This is ambient temperature is used for its installation temperature. The thermal expansion calculated using this ambient temperature. For example, we have 150 degrees operational temperature, and the ambient temperature is 10 degrees. So the temperature difference in this model is 140 degrees. This difference is used for calculating the thermal expansions of this model. For example, we can use the zero value. I'm not sure that I actually understand the question. I hope I answered it. Maybe not. Javier, please correct me if I didn't understand.
Well, it's 3 questions in the same. So maybe Pankaj, you want to unmute your microphone and make the question yourself. Pankaj, can you unmute your microphone?
Sorry, I have not asked any question actually. I don't know how it went. No, I did not ask any questions. It's fine.
Okay.
Okay.
Sorry.
Okay.
Sorry.
Hello. Hello. This is Pankaj Kumar.
Yeah. Hello.
Yeah, Alex.
Yes.
The question is, when you're setting this ambient here in this case, is it going to be the same as erection temperature? The reason is because you're evaluating the nozzle. So it's delta T that you're talking about. It will be simulating for the site condition, or you're setting as a fabrication which can be below normal ambient.
This temperature is the temperature of the piping system when you weld the last weld in this system, when the system became when you install this system. It's not fabrication.
Okay, that is the reason of the reason is you will appreciate that when we consider North Sea varies from very low temperature to positive something like 17, 18 Celsius. When you go to Middle East, you will have a very low temperature to a very high
Yes.
ambient. So
In Russia, we usually use minus 20 degrees.
yes,
It's standard temperature, installation temperature, and usually we use minus 20 degrees here. But I use 0 degrees because in other countries usually the other ambient temperatures are used. For example, in Russia, it's minus 20,
no,
standard.
Yeah, my discussion here is when you have minus 20, because you can't do the fabrication at minus 20. When you're talking about Russia, because I also work for a lot of the projects on Sakhalin Island. So the platform where this pipework is getting installed, all the structure and the empty pipework sees the same ambient. So here the
Yes.
question for me was, in your analysis, are you setting this temperature to low temperature because the fabrication will
No,
minus 20?
no, it's not lowest temperature. For example, we have minus 20 is installation temperature.
Yeah,
For example, this is operation temperature, but
yeah,
in some cases, the temperature can be minus 45 degrees, for example. So we need to create several operational modes.
yeah,
For example, in emergency situation, when the pipe is cooling down to minus 45 degrees, we can
yeah.
create the special load case for this. So we use ambient temperature for installation here, okay?
Okay. It makes sense.
So, okay,
Yeah.
okay. So now we have created the model, and let me check how does it work. It's already done. So let me check the deformed shape of this piping system. We already can see how does it work, but we didn't take into account the expansion of the vessel. For example, we have the vertical vessel here on the legs like this, and we have the nozzle. And when this vessel, it has a temperature, so we will have the thermal expansions in upper direction. So we need to consider it. How to do this? We can add here the thermal expansions. I'll add support movement, for example, 4 millimeters in vertical direction. Now I can run analysis, and we can check how does it work. You can see now this anchor is moving, and the left side, this position is installation state at ambient temperature. This middle position is operational state, and the right position is cold state. So in this model, the cold state and installation state is the same. So you can see how does it work. It's heating up and cooling down here. Okay, so in this model, for example, you can define the allowable loads for the nozzle, and if you run analysis, you will see that the loads on this nozzle is greater than allowable. You can open the restrained loads, and you will see that some loads are greater than allowable. But this is the rigid anchor. The loads will be very high. So how to make the more accurate model and consider the vessel flexibilities? What is the vessel flexibilities? We can have the local vessel flexibility like this, the vessel wall flexibility, and also we can consider the global flexibility of the vessel when all vessel is deformed under the applied loads. How to do this? I will delete this anchor and add here the vessel vessel nozzle. We have several elements like tank, pumps, inline pump, turbine, compressor, air cooler, fired heater. I will choose the vessel nozzle. So I choose vessel nozzle. I can add flexibility, but I will not do this right now. And I can check the loads. So you can specify manually the allowable loads here. If the, for example, vessel or any other equipment manufacturer give you the allowable loads, you can specify it here. Or you can check this nozzle using WRC code automatically. So I will choose this option. And now here I can specify the vessel diameter, material, and temperature. So also here I will specify the length from the nozzle point to the vessel anchor, for example here. So this length will be 2 meters here, this one. Okay, now let me specify the vessel parameters. It will be, the diameter is 1,200 millimeters, wall thickness 14 millimeters, the nozzle diameter, nozzle wall thickness, and shell length, for example, it will be 4 meters, and offset will be 0. It will be, the nozzle will be in the middle of the vessel. So the greatest flexibility is in the middle of the vessel between the any stiffeners like the vessel heads, bottoms, and stiffening rings and other. So this will be middle. The full length is 4 meters, and our nozzle will be in the middle of the vessel. So let me check on what, I'm sorry. I used the incorrect temperature, sorry. Okay. So I set the parameters of the vessel. So now I can run analysis. And we can check how does it work. You can see that nozzle is moving in upper direction because TopProf automatically calculated the thermal expansion of the vessel, and you can check the value. I click here and I see the displacement is 3.73 millimeters. This is thermal expansion of the vessel. So now I can open the nozzle and equipment loads, and we can check the stresses in operational mode according to WRC code. You can see here the stresses. So the stresses didn't pass the strength requirement, and strength requirement did not satisfy it, so it's failed. Now, what should we do? Let me improve the model. I will add the, sorry. How to hide it? Okay, I will add the T here. It will be Weldon T. I will take it from the database. I will use 20, this one. This is the length of the T and T height. So StarProf will automatically model the height of the T and the length of the T element. This used when the wall thickness of the T is greater than the connected pipes. Usually it happened if you use European code or Russian code. Now click OK. Also, you can see the stress intensification factors of this T here. And now let me check the analysis. Let me check stresses. The stresses are okay, no problem. This is primary stress from weight and pressure loads, and this is expansion stress. This is expansion stress, and this is allowable stress. So everything is okay here. You don't have any problems. You can check all the equations. But we have the problem with nozzles. We have the problem with a nozzle. How to reduce the loads. Let me add the global flexibility of the vessel. This one. And let me add the local flexibility of the vessel. How to do this? I open the nozzle properties and select here WRC flexibilities. You can see the flexibility values was automatically calculated according to WRC code. Also, you can add it manually, and you can calculate it by finite element method. I will show it later. So now I will calculate it using WRC code. We can run analysis. This is only local flexibility. There is no global flexibility at this moment. But now you can see that nozzle is rotating. Like this. You see the axis is now not horizontal. We have the angle here because the local flexibility taken into account. And also we can check the nozzle loads. It was 1.3 thousand%, but now we already have 400%, so it's much lower. And now let me add the global flexibility. How to do this? There are several ways. I will use one of them. I will add the rigid element here. The length of this rigid element will be half of the vessel diameter. Unit weight will be 0. And we will consider the thermal expansion. And at this point, I will add the cylindrical shell element to model the vessel. For example, -2 meters, the diameter 1.2 thousand millimeters, wall thickness, for example, 14, the pressure and temperature of the vessel, and where will be the water inside. Okay, and we can add the anchor at this point. Now let me run analysis. Now automatic calculation of nozzle thermal expansion is impossible because it will be automatically taken into account by thermal expansion of this cylindrical shell. Now I run analysis. And let's check how does it work. Now you can see I have the vessel with the nozzle, and the nozzle is rotating around the vessel. Let me show you. you can see that this pipe is rotating. This angle is not zero. So StarProf take into account the local flexibilities of this vessel. And also it take into account the thermal expansion of this vessel and global flexibility. But in this model, we will not see how does global flexibility working. So I will demonstrate it. I will add the anchor here at this point and increase the length of this pipe to demonstrate you the global flexibility. What is the global flexibility? Run analysis. You can see here, this is the local flexibility of the nozzle. I will switch it off. It will be rigid nozzle. Now I run analysis. And now we will see the global flexibility of the vessel. As you can see, now the nozzle is rigid, but the vessel is flexible. And you can see that vessel is moving here. Okay, so let me return back. I will undo the changes. Okay. So now our vessel has the global flexibility and local flexibility. We can increase the length of this pipe, for example, to 3.8 meters. And let me run analysis. Let me check the nozzle loads. As you can see. Yeah.
Can we ask questions now? Like
Yes,
in between?
yes.
Yeah. I
Yes.
was just wondering, can you actually export this data to an FEA package? Let's say if you want to do simulation in ANSYS or Abacus, where sometimes you need to do maybe some corrosion or specific local damage analysis for fitness for service. Is it possible to export these models in a FEA package?
We have a special converter to ANSYS. You can export the model to ANSYS. But,
okay.
But it is not, it's not, how to say, it's a special converter. It's, it can be used for request. We can send it to the user because it is not built into StarProf user interface right now, but we have the converter to ANSYS.
And how, for example, like I've used in the past Caesar 2, quite some time back, I might add. How do you feel like you are better or different than Caesar 2 when it comes to pipe stress analysis?
For example, in Russia, Caesar 2 is not used at all. Mm-hmm. All 3,000 companies use StarProf, and almost none of them know what is Caesar 2. Nobody knows what is it. Everybody know only StarProf. So StarProf is software that is used for since 1965 in Russia. But Caesar 2 was appeared in 1985 in other countries, but Russian people didn't know anything about it. We always used StarProf. So I'm the developer of StarProf, so I can't tell you my feeling from using Caesar and StarProf. But I think that StarProf is more easy to use and more quickly. But this is my opinion, like the developer of the software.
It looks very nice. So looks very nice, to be honest. And where are you based at the moment, if I may ask, Alex?
What again, please?
Where are you based at the moment, Alex?
Where me what?
Where are you living at the moment? Yes, in country.
I'm living in Moscow, Russia.
Moscow. Excellent, excellent. So I'm based in Scotland. I'll let you continue with the demonstration, and if I have other questions, I'll send you an email. Please continue.
Yes, of course, you can send me the email. My email is, let me show you. Oh, sorry, I will put it here.
Remember, you can also use the discussion in the workshop, because this way the question, if they are not if they are like public questions, you can use the discussion in the workshop. But if they are private, of course, please use the email. Okay.
Yes,
No
yes, you can use this email for private questions. And also you can download the demo version for free for 30 days on demo.pursuit.com. And you can try the software. Why they do this? Because till 2015, the software was only in Russian language. So nobody knows about our software outside of Russia. But in 2015, we translated into English and Chinese languages. And in 2018, we start our marketing company. At this moment, we already have about 200 users in China and a lot of users in other countries, but not so much as in Russia. But number of our users is growing. So because we entered the worldwide market just 2 years ago. Okay.
Excellent. Thank you for that.
Okay. Okay. So this is very. This question is oftenly used, oftenly asked by people, because nobody hear about the StarProf software before. Okay, so now let me show you how to add the legs for this vessel. For example, you can add the legs. Let me do this. We add the rigid elements. Like this. And also we'll consider the thermal expansions. Okay. I will not comment what I'm doing to speed up the working process. One moment. Okay. So now we can add the legs. It will be cylindrical shell tool. For example, 70 by 6. And the length will be 1 meter. Oh, sorry, the direction is wrong. -1 meter. And add the anchor on the end of this leg. Now I will copy it using Ctrl-C and Ctrl-V. Okay. Now our vessel have the legs. I can save it and run analysis. You can see how does it work. Like this. And let me check the nozzle loads. And now you can see that after the add the legs, our nozzle passed the strength requirement. So now everything is okay. Our nozzle is fine. No problem. Also, we have another option. We have Nozzle Fem software. Let me show you. Let me show this software. This is Nozzle Fem. It allows to check the nozzles using finite element method. This is also the PASS software. It's included into the PASS package. So we can create the vessel model using, for example, ASME division 1. We have another codes here. We can calculate the flexibilities of the nozzle. We can calculate the allowable loads. I will define the base element. It can be horizontal vessel, vertical vessel, storage tank, pipe to calculate the non-standard T's, for example, with diameter to wall thickness greater than 100. It is restricted by ASME B41 free code. You can calculate it using finite element. We have conical shells, conical heads, elliptical heads, and some other elements. We have a bend. It can be bent with trunnion, for example, like this, and rectangular plate, like this. So at this moment, I will use the vertical vessel model. It will be 1.200 millimeters or 1000 millimeters wall thickness, and the length will be 4,000 meters. The nozzle will be like this. Wall thickness 4.35. And this will be 2000 millimeters. Let me check the steel from steel database. It will be ASME database. For example, I will take this steel. Okay. I take it into the local database. Select here and select it for the base element. Okay. Now we can specify any. Let me change the units. Okay. You can specify the loads here. For example, you got the loads on this nozzle from StarProof software. I will show you here. This load values, and you can write it and type it here into this field, and Nozzle Fem will calculate the stresses in the nozzle with applied forces that can be taken from StarProof software. So now let me run analysis. I will save the model. This is finite element analysis. This is the matrix. Okay, analysis is done. This is input data. You can now save this report into Microsoft Word, for example, and print this. This is strength check according to ASME division 1. This is finite element model and all the checks. So all the strength check are satisfied. We can have the allowable loads for this nozzle, and we can use these allowable load values in StarProf, for example, we can calculate allowable loads using finite element and type it here and use it in StarProf software. And also we can calculate stiffness and flexibilities using the finite element method, not WRC code, but this is WRC stress check, and this is flexibilities calculated using finite element method. We can use these flexibilities here. You can choose manually and type it here. In the next version, we will combine two softwares, StarProf and Nozzle Fem, and you will be able to define the model right from the StarProf interface. At this moment, it's two separate software. Okay, so now, for example, you can check in 3D how does it work. Let me show you the 3D model. Okay. Here you can see the 3D model of the nozzle, and you can see the deformed shape, for example, and so on. Okay, so I close the software and let me return to StarProf. Okay, now the next point is how to analyze the pumps. For example, here we have the pump element. How to do this? I will delete the anchor and add the pump by APA 610 standard. This is the pump element. We can consider the thermal expansions of the pump. You can specify the shaft axis. It will be Y direction. This is the pump center coordinate from the node 7. Let me show you the drawing. Okay, for example, we will consider this pump. So this is our nozzle. The distance will be 273 millimeters. Let me enter here, 273 millimeters. And then node 7. This code has the API 610 code, has the allowable loads table, but in some cases we can use the advanced checking algorithm in Appendix F, but we can use it only if we have two nozzles. At this model, we have only one nozzle, so we can't use the double values in this table. So I need to use, I can't use the double values of the table, so I will set here the 1.0 value. Okay, this is the pump. I will copy this pump into this node. Oh, sorry. Paste it here. And specify the node 4. Okay, node 4. And this value is 1. Okay, now we can run analysis. And we will see the loads on the pump. As you can see, the loads are very big. This value is double of this value. This is allowable value, and this is acting value. It's axial load on the pump nozzle. And here we have the problems too. So if we will use the double values of allowable loads, maybe we can pass the check. The pass the API 610 check. How to do this? We need to add the second node. Let me do this. I select this node, use tools, and insert independent node. The coordinates will be, let me check, 273 and 300 millimeters. 273 and 300. Oh, sorry, it's meters. Undo. 0.273 and 0.3. Okay, we have independent node, and we can do the same at this point. Okay, and now let me copy the model. I will select this part of model, copy it into clipboard using Ctrl+C, and then paste it here. And now combine these two nodes. Okay, so we have the model like this. After that, I will add the pipe. For example, it will be 3 meters. And then we'll go down for 1 meter. Oh, sorry. -1 meter. Okay. And I will put anchor here, for example. This is not real model. I'm just creating it in real time. So now let me connect this pump to the second nozzle. It will be node 22. Okay, now two nozzles are connected. And let me connect the second pump. And now I have a right to use the value 2 here. So allowable loads will be multiplied by 2. And in this nozzle too. Okay. So now let me save the model and run analysis. Let me check the deformed shape. How does it work? Our system is working like this. And you can see StarProf take into account the thermal expansion of the nozzle. You see this node is moving. And let me check the nozzle loads. Equipment loads. So now you can see that our nozzle, this nozzle in node 7 has the strength requirement. So we don't have any problem here. But we have the problem with the second node. This is node 7. This is node 22. This is node 7. Here is node 7. We don't have any problem here already, but we have problem here. So we need to improve this model. How to improve it? Okay, let me think 1 moment. Okay, for example, let me increase the length of this pipe to add more flexibility. I will set the base node here, and now I can change the length to, for example, 3 meters. After that, I can change this pipe and this pipe, for example, using the side panel. And we can, for example, add the spring at this point to hold the weight of this pipe. I will add the spring hanger. Let me choose the spring hanger table. It will be, for example, Lisega. So now let's check our model. Let's check nozzle loads. And now, bingo, you can see we don't have any problem. So our system is working. All the pump loads are okay. We have, this is the sum is 40%. Don't have a problem here. And we don't have the problem with vessel nozzle. So we have our model is working. So now we can optimize it, for example, change something. But I will not do this because it's just demonstration. So now we can, for example, we can consider the ASME B31J flexibilities of the T's and more applicable the stress intensification factors. How to do this? Let me demonstrate it. For example, I will add 2-meter pipe. At this point, it will be restrained between 2 anchors, and I will add the node in the middle and 1 pipe by x-axis, like this, and I will add anchor here. So we have 3 pipes restrained between anchors. I will add the welding T. Here is the welding T. And I will reduce the branch to, I don't remember, for example, something like this. It will be reducing T. So now let's check the, now let me add here another pipe. For example, it will be vertical pipe. To have the outplane moment, I will add the outplane moment. And copy the band here. It will be long band. Okay, now let's run analysis and check the loads on this anchor. Let me check it. The restraint loads on anchor 33 is like this. I will save it here. I made the screenshot. And let me check the stresses in this T element. I will check stress. The T element is 31. Okay, this is 31T. Let me save the stress value. This is expansion stress and sustained stress. Okay, so now how to add the ASME B31J. I just open the project settings and check this option. Use ASME B31J. And now I can run analysis again. So now let's check this anchor load. It's anchor 33, and let's compare it with the load value that was before. So you can see that loads are lower. It became lower. And now let's compare the stresses. The stress in 31 point Where is it? Here is it. Okay. Now let's compare it. Here is, oh, sorry. Okay. This expansion stress was like this, and now it is much lower. You can see, because we use more accurate stress intensification factors according to ASME B31J code. So now the stresses are lower. How StarProf deal with T's? Let me open the help system. Okay. StarProf automatically add the special nodes on the each end of the T element and use the increased wall thickness if you will define the increased wall thickness. Usually this happens in European code and in Russian code. In ASME code, usually the wall thickness is the same as the connected pipes. Also, StarProf add the rigid element with length of half of header diameter, and also StarProf add the flexibilities of the T. It add 2 springs on each side of the header to consider the flexibilities of the header, and it adds the flexibility on the branch. And the value of that K factors is calculated using ASME B31J code. Okay, so each T is automatically converted into the more accurate model each time when you run analysis in StarProf. So now let me switch off the ASME B31J. And now let me show you another feature. I will show you the tank model, how to model the tank. Let me add the node on this vessel, and I will add the pipe, for example, by X direction. It will be 30 meters. I'm sorry, by X direction, 30 meters. Okay. And now I copy this nozzle into this point. Now you can see I didn't add the rigid element here. I just copy the nozzle right inside this point. StarProf is smart enough to add the rigid element automatically. So you don't need to use rigid elements because StarProf will automatically add the rigid element in this situation. So you can just put the nozzle element into intersection point between 2 pipes or pipe with a cylindrical shell. StarProf will automatically add the rigid element, so you don't need to care about it. I just show this because Caesar 2 users usually add the rigid element, but in StarProf you don't need to do this. You can just add the nozzle into intersection point between 2 pipes. So let me add the pipe turn here by Y direction, for example, 1 meter minus 1 meter. I will copy the band And I will add here the tank element. Here is the tank. I select the temperature of the tank, the radius, for example, 50 meters. The length from the bottom will be 300 millimeters. Wall thickness 20. This is the diameter of the nozzle. Filling height, for example, 5 meters. I will not add the tank settlement at this moment. And also you can add the flexibilities according to API 650 code, and you can check allowable loads according to API. Of course, you can set it manually, or you can use another codes, but I will use standard API allowable loads. So we have a tank. And let me add the expansion loop at this point. It will be 2 by 2 meters. And add the bend elements. Okay. Now I add the resting supports. This is the first resting support. And here I can add several resting supports, each 2 meters, like this. And the same at this pipe. Okay. So now let me run analysis. You can see how does this expansion loop works. This is vessel and this is tank. Now we can check, and you can see that this pipe rotates. It rotates in vertical plane. Why? Why it happening? This happening because the bulging effect in the tank. What is this? When you fill up the tank with the fluid, the tank wall deforms like this, and this nozzle rotates in vertical plane. So StarProf automatically take into account this effect, and also the nozzle moves outside of the tank axis. Okay. So now also StarProf consider the thermal expansion of this nozzle, and StarProf can consider the nozzle, the tank settlement. How to do this? You can specify the tank settlement in the tank properties. Here, you can specify the tank settlement. So now let me check the nozzle loads. You can see the tank nozzle loads here. Everything is fine here. We don't have any problem. The loads pass using API 650, and also you can analyze the tank loads using the finite element method. You can use Nozzle Fem software to check the nozzle loads, because some companies think that allowable nozzle loads by API 650 code is not accurate. So you can use finite element method. This is the Nozzle Fem software, and you can analyze the loads on the tank nozzle using finite element method. you will see the model like this, and Nozzle Fem software will show you all the strength check of the tank nozzle using finite element method. Okay, so now let me add the tank settlement, for example 100 millimeters, and now we can run analysis. And now you see we had the problems with the nozzle loads, and let me show you a deformed shape. You can see this is the tank settlement, and this support don't let the pipe to go down, so pipe rotate around this support. We need to remove several sliding supports near the tank nozzle to add the flexibility. So this leg will take the deformations from the settlement and add the flexibility to the piping system. So now let me run analysis again. Okay. And let me check how does it work. So now pipe can move down, and let me check the nozzle loads. We still have the problems, but we can increase the flexibility of the model. For example, I don't know, maybe we can increase the expansion loop or something else to improve the flexibility. Also, we can add the support at this point. Okay, let me check. Oh, now we have no problem. So now our nozzle passed the strength requirement. Now our model is perfect and it will work because all the nozzle loads are satisfied the code requirements. Okay. So now let me show you how to define that only one pump working at the same time. How to do this? We have the special operation mode editor. Here is the operation mode editor. I will add two more operational modes. This left pump, I will call this left pump, and this will be right pump. Okay. Now we can add, for example, valve at this point, and valve here. I will add valve element. We can check the flange leakage check for the valve, but I will not do this right now. It's possible, but I will not do this. Okay, we have two valves, and now I check the current mode, the left pump. This will be current mode, and now I can select this part of pipe and set here the zero temperature, not zero, maybe 20 degrees, and zero pressure. After that, I change to the right pump and select this part of piping. And change the temperature and pressure. Okay, so now let's check what we did. I will open the color diagram and I open the temperature, for example. So now you can see this is 20 degrees and this is 150 degrees. And now I change to the left pump, the opposite situation. Here is the 20 degrees and here is the 150 degrees. And this mode, then both pumps working. Usually we use this model with both pumps working for hanger sizing, because hangers can be sized only for one mode. Usually we use the first mode for that. Okay, so now we can run analysis. And we can check the deformed shape. I like the deformed shape because it allows to see how does model working immediately. This is operational mode. As you can see, both legs, thermal expansion are the same. Now I change to the left pump. As you can see, this pipe expands, but this pipe not. So this valve is higher. And now right pump working. Now this leg expands. So let me show you difference. Both legs, thermal expansions taken into account, only left pipe and only the right pipe. So we have 3 operational modes with 3 different temperatures. Now you can check stresses. This stress is in first operational mode, primary stresses, expansion stresses. This is the left pump working, primary and expansion. And this is right pump working, primary and expansion. This is the standard sustained stresses, and this is alternative sustained stresses. It's a new requirement of ASME B41 code. When we calculate allowable stress range, we need to consider several positions, several modes of a piping system with switched on or switched off some supports, because some supports can switch off in operational mode. So StarProf automatically do this, and you can see the standard and alternative sustained stresses according to requirements of ASME B41 code. And StarProf automatically use the maximum sustained stresses from all the conditions. It is done automatically. And the same way, you can see the maximum stresses from all operational modes. The maximum is the maximum from all 3 operational modes. And the same with equipment loads. This is equipment loads from operational mode and left pump working. So now you can see we have the problem here. And this is right pump working. Okay? This is how StarProf considers several operational modes. You can open any pipe properties and click the button L button, and you can see the value of the temperature in this pipe in different operational modes. Then the number of operational modes has no limit. You can create, for example, 100, 1000 operational modes, so you will have 1000 temperatures, for example, or 1000 pressures. There is no limit. So now let me move to the next topic. Let me save the model, and I will create a new model and show you what is the cold mode and what is the how to avoid the zero anchor loads from piping. I will use B31.4 code, and also I will show you how to model underground piping. Let me create the pipe with length about 30 meters. I will not use the database at this time. I will just type myself, material, pressure, temperature, for example, 90 degrees, fluid weight. Okay. We have the model like this. I will add 2 anchors, and I will add the expansion loop in the middle. Okay, I will add the bands. Okay, now I add the supports. Okay, our model is ready. So now let me demonstrate you one interesting feature. Let me run analysis and see the deformed shape. The left position is installation state, middle position is operational, and right position is cold state. So now let me show you the animation. As you can see, the pipe doesn't return to initial position. This is installation state here, and this is cold state. In cold state, pipe doesn't return to initial position. So when pipe heat up, this point moves in lateral direction, but when pipe is cooling down, it is trying to return back, but it can't return because friction forces doesn't let the pipe return back to installation state. So the piping system never returned to its initial position. Let me show you. Okay, for example, you have the pipe like this. This is anchor and free end, and we have the sliding support. Then the pipe heat up, it moves in right direction, and friction forces acting in left direction. But when they cool down the piping, it moves to the left direction, and friction forces change their direction. And the friction forces doesn't let the pipe return to its initial position. So in cold state, you will see the support loads. It will not be zero. In some cases, it can be important. And also, we need to calculate the expansion range between operational state and cold state, because it's greater than expansion stress between installation state and operational state, like this. This stress range sometimes became greater than this stress range. So StarProf can check both of them. Okay. So now let me show you the difference of working of this expansion loop with friction and without friction. I will add the second operational mode, and I call it no friction. And select the friction multiplier 0. In first mode, we will use friction multiplier 1.0, and in second, it will be 0. And now let me run analysis and see the deformed shape. This is deformed shape of the pipe with friction. You can see that the nodes, these nodes, is not moving in a lateral direction, and this is mode without friction. The difference is huge. The displacements are greater without friction. And also, as you can see, with friction, pipe never returned to its initial position. But with friction, but without friction, the pipe always returns to installation state, as you can see here. This is with friction, and this is without friction. So usually when we consider the wind loads or seismic loads, we use the friction multiplier 0.5 or even 0. Okay. Now I will delete the second mode. And now let me copy this model like this, using Ctrl+C, and paste it here. Now we have two expansion loops, absolutely symmetrical. What will be the axial load in the node 1 and this anchor? Let me check. The load will be 0. Load is 0 because two expansion loop has absolutely the same thermal expansions. So the load from left side and from right side are the same. And some of the loads will be 0. In Russian codes, we have a special requirement to use the special trick in such situations. The requirements is following. We take the load from one side on this anchor minus the load from the other side, but multiplied by the special factor. Usually this factor is 0.8. So for example, if M is 10 tons, we will have 10 minus 8 tons, we will have 2 tons. So now I can move to support local axis. You see the anchor factor is 1.0. We have 0 value here. But if I will use 0.8, this value became non-zero. And we can check how it was calculated. This is the equation. This trick is required by some codes, some Russian codes, and it's widely used to quick estimation of loads on the intermediate anchors, because some part of the piping system can have slightly different friction factors, or for example, if you fill the pipe with hot fluid, firstly the right expansion loop extend, and only after that the second expansion loop extend, and you will have non-zero load at the first stage when you just fill in your piping system. And also, for example, the sun can shine on this part of piping, and this part will be slightly lower, will have slightly lower temperature, or some other situations. And in real life, the load on this support will not be 0. It's of course you can check all the situations, change the temperatures, change the friction factors, and change everything in this model, but it will take a lot of your time. So this trick with the factor 0.8 is much more easy to use for approximate solution during the piping design. So it's, as I said, it's widely used by Russian companies. And the next topic, let me check. Oh, okay. It's how to model the buried piping. Let me add the buried piping model. I will add 0, for example, 1 meter pipe. Oh, sorry. Okay, we have 2 meter pipe, and now it will go down underground. I will add the next pipe in minus 0.5 meters. This will be the entry point underground. Now I add the underground pipe, 1.5 meters, and I check this checkbox, pipe is buried. We will have the soil tab here, and here we can specify the soil properties from database. For example, we can take some predefined soil from database. This is the depth of the pipe at the node 37 and node 38. We can model the water, model soil movements, and some other features. We can add the insulation flexibility. For example, polyurethane insulation flexibility to this piping model, or pipe can be without insulation. And also for polyurethane foam insulation, we can add the expansion cushions. The expansion cushions add the additional flexibility to the pipe turns, and usually it's used for district heating networks. So I will not use it in this model, just model without insulation. Okay. So this pipe is buried. And now I add the next pipe by y direction, for example, 300 meters. It will be a very long pipe. And temporary, I will add anchor at this point. And now I will demonstrate you what is restrained pipe and what is unrestrained. For example, ASME B41 free code has different stress check equations for restrained pipes and for unrestrained pipes. I will break this pipe by every 2 meters. I will just add a lot of empty nodes and run analysis. Now, if we will check the deformed shape of this piping system, let me run analysis. You can see the nodes moving. These nodes are moving, but if I will look on this pipe globally, you can see that only part of this piping is moving. So to about this point, this part is moving. It's LA zone, it's sliding zone, but this part is restrained. It is not moving. So we need to use unrestrained equations only for this part of piping. This is unrestrained part of piping. This part is restrained, and the rest of the piping is semi-restrained or partially restrained. We can call it partially restrained. So the code requirements is to check unrestrained using one type of equations and unrestrained, and restrained pipe using another equations. But what to do with partially restrained pipes? Usually we use unrestrained equations, but in this zone near the restrained zone, you will have the problems because these equations will not pass the strength requirements. So start-off has the special ability. It is, let me show you, in project settings, we have the restrained, unrestrained. You can specify manually if you choose this option, and for each pipe, you can specify which equations to use, restrained pipe or unrestrained. But it's too hard because you don't know where is restrained part and where is unrestrained. We have another feature is auto detect. StarProf automatically check the axial load, internal force in the pipe, and if it's almost close to restrained pipe, it will use the equations for restrained pipe. And if it's lower, StarProf will automatically use the unrestrained pipe equations. But the best solution is used start smart check calculation. The idea of this calculation was taken from Russian code, and we slightly modify the original strength check for ASME B414 code. But it's not against the code, it's following the code, but the equations is applicable for any type of zone, restrained, partial restrained, or unrestrained. I can't explain it right now because it will take about 1 hour, so you can just read my article about this, about the start smart check function, how does it work. I will just show the result that stresses are checked automatically for any part of piping. So you don't need to specify manually where is the restrained pipes, where is unrestrained. You just draw your model in StarProf and check the stresses. That's all. So you don't need to do something manually. Here is the stresses. This is the unrestrained part, and this is restrained part. You can see that didn't pass the strength requirements. So now let me reduce this pipe. I will delete all empty nodes and reduce the length of this pipe to 30 meters. Now I add the anchor on the end of this pipe. I will delete the anchor from this point and copy the bend. Okay, now I run analysis, and now you can see the soil springs that was automatically placed by StarProf, and you can check how does it work, how does our model working. You can check stresses in the model. Everything is fine here. And for example, if we'll have the problem with this band, you can add the expansion loop, for example, the same way as you do this for above ground piping, like this. This is the soil surface, and run analysis again. You will see now StarProf place the soil springs in different way, and now we can check the deformed shape of this piping system. We can check the stresses in this piping system, and also StarProf allows to add the soil subsidence. For example, if we have permafrost soil, some part of soil can the ice turn to water, yeah, and the subsidence of the pipe happening. So you can specify it in StarProf. You can add soil movements, and all the soil springs moves down, or it can move up, or it can move in any other way. For example, to model a landslide, StarProf allows to do that. I will not show it right now because it will take a lot of time. So I think I'm already out of time. Javier, do I have any time, any additional time or not?
Yeah, thank you, Alex. Actually, you have used around 1 hour and a half. I think it's been very illustrative and very interesting, your demo of the software. If you want to, maybe attention is dropping after a while in the attendees. Maybe it's a bit it's a bit long. So if you could maybe use some slides to show something, but finishing in 5 minutes, that would be great. Okay, Alex.
I think that I don't have a time for other topics, so maybe I can answer the questions.
Yeah, we can start questions and answers. Yes, that's great.
Okay.
Maybe the best way is to use the chat, because that way, it's with so many participants, it's difficult to. And if anybody has questions, maybe you are welcome to use the chat, or
okay.
If you want to unmute your microphone, also maybe you can try to unmute your microphone and go ahead and make the question.
So I already see that some people ask the questions. Is it possible to model the structural steel? At this moment, no, but we will add this feature in the next year. I think in next year we'll add the beam elements to StarProf. It's quite easy, but our domestic users never asked for it. So, but some international users ask for it, so we will add this feature. It is not so hard for us. What about the region? Yeah.
Sorry, I have also received another question to me. Is it maybe it's the same one? Is it possible to add small sections of a structure steel to incorporate stiffness of supports?
No. At this moment, you can't add the beam elements. In the next version, we will add the structural beam element here, but at this version, no. The only way to consider the steel structure flexibilities is to add the non-standard restraint and add the springs, 6 springs with the flexibilities of structural steel. Some companies usually use this trick to model the steel structure flexibilities. They analyze the steel structure in some special software for steel structure analysis, calculate the flexibilities at the points where the pipe supports or connected to the steel structure, and specify here the flexibilities of steel structure. But at this moment, we don't have the beam elements. But the steel structure can consist not only from beam elements, it can consist from plates or other elements. So it is not so easy. We can only add the beam elements. Okay.
Okay.
Next.
There's another.
Yeah.
Sorry. Have you already replied the tank bulging displacement from Stephen Edelman?
No, I didn't answer this, so I will answer.
I can read it. I can read the question to you if you want. Can the software also calculate the tank bulging displacement, or does this need to be input as a separate displacement at the nozzle interface?
StarProf automatically calculate the tank bulging displacement. When you add the fill-in height here in the tank properties, StarProf automatically rotate the nozzle, the tank nozzle, it automatically rotates the tank nozzle and automatically move the nozzle. So you don't need to calculate it manually. Everything is done automatically. If you will change the filling height, StarProf will automatically model the bulging effect in different, it will calculate the different values. For example, if you have several operational modes, this is main mode. For example, another mode can have a different filling height, for example, 10 meters.
Okay, there's a square, Alex, blocking the view of your computer between the orange tank and the pipes. I don't know if you can move that. Yeah, that square. I don't know exactly what it is. It's a rectangle. Try to move something next. Now it's no. It's. Do you have some window on top of the square?
What?
Anyway, don't worry. It's okay.
I have chat window. Do you see the chat window?
No, chat window is blocking the view of it.
Okay.
That's it. You have removed it now. Yes, thank you.
Okay.
I can read that for you. The next question is from Morteza. How does this software deal with water hammer surge? May water hammer pressure, which is within the design pressure of the piping, cause a problem to the system?
Yes. Let me show you. For example, we have the model like this. One moment. The model like this, and we need to consider the water hammer effect. I'm sorry, I don't have a time to show it right now. I'm already out of time, so I will just show the video. You can save this model and open this model with another software that is called PAS Hydro System. It's also the PAS software, and I hope the video will work fine. So you can save this model, and PAS Hydro System software can open this model. This is PAS Hydro System software. It can calculate the water hammer loads automatically. For example, this valve is closed very quickly, and this causes the water hammer effect in this piping system. So the Hydro System software can calculate the surge effect of water hammer, and it will calculate the load values. But the main idea is that Hydro System software is 3D software. It can calculate the loads in 3 dimensions, in X, Y, and Z dimensions. So it calculates the loads at each moment of time, but happening that applying at each band, at each moment of time. For example, 1.3 seconds, 1.4 seconds. The software will calculate all the forces, all the unbalanced forces on all the nodes at the same moment of time in 3D space. And it automatically finds the most dangerous values and save it in the special file. Now I will show you the start software. We have this file that was exported from PAS Hydro System software. Now we can open, sorry, this WebEx window don't let me to work. Oh, okay. Now we can open operational mode editor, open the second mode, and add the loads from file from Hydro System. As you can see, we added H additional forces at the time 0.02 seconds, 0.07 seconds, and other in different moments of time. The most dangerous moments of time is automatically found by hydro system software. We have a special algorithm that finds the most dangerous moments of time. So now we can run analysis of this system and check it for the loads applied from the water hammer effect. This is operational mode, just thermal expansions. And this is water hammer load. The first case, the second case, the third case, and others. You can see here different options. And if you will check, for example, the moment of time 0.07 seconds, you can open the band properties and you can see that StarProf applied two forces to this band. But if we open these band properties, you can see that at this moment of time, StarProf applied another forces. So we don't apply only one force in one band. We apply all the forces, but is acting at the one moment of time, at 0.0 seconds. And for each moment of time, we apply different number of loads. So this is done automatically by StarProf. We have a video on our YouTube channel. There I demonstrate this model in more details. I'm sorry I don't have time right now to explain everything, so you can watch this video and check it. Okay? So another question,
okay,
please.
Thank you. There's another question. Can you take into account seismic loads?
Yes, we can take into account seismic loads. Let me show you. For example, we have this system. Let me remove unnecessary operational modes and let me add the seismic. I will add, for example, it will be user-defined accelerations in 3 axes, X, Y, and Z. After that, I selected, I will apply it to the first operational mode, but I can apply it to any operational mode or even several operational modes with different temperatures can have the seismic loads. So now let me check the pipe properties. Okay. Okay, okay. So I think now we can run analysis. And the most easy way to check to see the seismic effect is to check the deformed shape. So I will just show you the deformed shape. This is seismic load by X direction. You can see how does it work. This is seismic load by Y direction. And this is by Z direction. Okay. Another question, please.
Yes, thank you. It's how does this software calculate natural frequencies of a piping system?
This is the problem right now because StarProf doesn't have a dynamic model. It can't calculate the natural frequencies, but we're already working on it. And the next version that will come out in this year, before the end of this year, StarProf will automatically calculate the natural frequencies. Here is the dynamic options. And after we will finish it, it's already working, but we are testing it, and several companies right now testing this feature. And after the tests will pass, and after verification, we will issue the new version with dynamic analysis. It will be very easy. You will just need to open operational mode editor and select the operational mode where you want to calculate natural frequencies. You will select this mode, run analysis, and after that you will see the natural frequencies in this menu, and you will see the mode shapes. At this moment, in this version, we don't have this feature because in our domestic market there is no such requirement, and it's a very rare situation when companies need to perform dynamic analysis. Usually we use another software for that, but for international companies, we add in this feature, and as I said, it will come out in this year. We will have the dynamic ability in StarProf, and it will be very easy to use. Just select the option and run analysis, and you will see the natural frequencies. Okay?
Excellent, excellent. And one more question from the same gentleman, Morteza. What is the requirement for natural frequencies of a piping system? Maybe this is too long, or maybe you want to...
What is the requirement? There is no requirement in StarProf because StarProf has everything that is needed. We have the weight of the pipe, weight of insulation, weight of fluid, and we have additional weight loads and additional non-weight loads. So all the weight loads is automatically converted into the masses, and non-weight loads will not be converted into the mass. So everything will be done automatically. You don't need to convert the mass manually. StarProf will do everything automatically, so it will be very easy to use. Just draw your model and run analysis. Okay?
Okay, thank you, Alex. I believe it's a good moment to finish your seminar, your workshop here, because we've already been here for 2 hours now. So maybe, of course, if there are any other questions, they can reach you either if they are public questions, they can send them through the workshop Telegram bot or webpage, or they can reach you in your email. Okay.
Yes, I'm always open, so you can ask me the questions in using any source like Telegram, like email, everything.
Excellent.
Okay, thank you. Thank you for your attention.
Thank you very much, Alex, for your wonderful workshop. Bye-bye. Take care.
Bye-bye.